Hello everyone, I'm going to talk about Bayesian optimization with categorical and continuous variable. My name is Nguyen. I am a machine learning scientist at Amazon. Throughout the talk, I will first provide a brief introduction about Bayesian and some illustration. Then we move into the main part of the talk, mixed categorical-continuous optimization and two advanced settings in dealing with high-dimensional data and population-based automated reinforcement learning. The popular example of Bayesian optimization is for hyperparameter tuning. So we may know that the machine learning algorithm performance will depend critically on the hyperparameter choices. So the task is to find the best hyperparameter for the highest performance. Traditionally, we can use grid search and random search to find the best parameter by considering all of the possible combination of these parameters, evaluate all of them, and pick the one with highest performance. But both grid search and random search are inferior. For example, in this, we have the best hyperparameter located at bottom left corner. Both grid search and random search will fail to identify that optimum location. On the other hand, the technique we are going to talk about today, Bayesian optimization, will be more intelligent. Since Bayesian can learn from the historical data to make informed decisions, and by that way, it can successfully identify the optimum location. Recently at NeurIPS 2020, there was a Blackbox optimization competition, and the top 20 winning teams are on using Bayesian. You can see that Bayesian optimization is currently the standard method for Blackbox optimization. In Blackbox optimization, we consider the relationship from input X to output Y is through the Blackbox. With different input X, we have different output Y, and we want to learn from the underlying relationship between these observations to identify the unknown maximizer of that function. And this is the task we are interested in solving in this talk. There are some properties of the Blackbox function. We don't know the function form nor the derivative. The function is expensive to evaluate, and we know nothing about the function except observing a few evaluations. So you can see that we cannot use a gradient descent method to solve this problem. Instead, we need more advanced machine learning method. Bayesian optimization is one of the machine learning methods for optimizing the Blackbox function. It optimizes the function by making a series of evaluations such that the optimum of f is found using the fewest number of evaluations. The question now is, how can Bayesian make a suggestion? It's gonna rely on the surrogate function and typically a Gaussian process to learn from the underlying function given a few data points. So here, given 3 observations at the red dot, a Gaussian process can provide the prediction as the expected function value, which is the black dashed line. This indicates how we may think the function behaves given the data. Additionally, Gaussian process also gives us the uncertainty estimation at the shaded area. The uncertainty indicates how the model is unsure in each prediction. And based on these two quantities, Bayesian will make the decision using the acquisition function, which integrate the two criteria together, and this criteria can be understood as the exploration and exploitation in decision making under uncertainty. As the algorithm proceeds, it will collect more and more data, and by that way, the surrogate function will be updated, and we can estimate the expected function value. And at the end of the day, Bayesian can successfully identify the optimum of the function. To see how Bayesian works in practice, let's look at this simple demo where I assume that we try to optimize the best learning rate for the highest accuracy for some of the machine learning models. And by randomly trial 3 data points, we got 3 observations at the red dot. We are looking at finding this unknown maximizer. And please note that we do not know the Blackbox function as the Blackbox here. Bayesian will carefully select the next point to evaluate. After Bayesian select a data point, we're gonna evaluate the Blackbox, observe the output. Using that input and output, we refine Bayesian models so that it can suggest better in the next iteration. And Bayesian will keep doing that for a few iterations until we hit the target or we hit the optimum. In this example, after 8 evaluations, Bayesian can successfully identify the global optimum of the function. And we can see that Bayesian spend more samples around the promising location, and it spend less sample as poor location. Since the goal is to find the global optimum using the fewest number of evaluation. After a brief introduction about Bayesian, let's move into the main part of the talk today, categorical-continuous optimization. Previously, our Blackbox function have the continuous input act. However, in practice, there are many situations that we need to deal with both the categorical and continuous variables. For example, in tuning hyperparameters for deep neural network, we have the continuous variables such as the learning rate, the weight decay, and we have the categorical variable. They are the optimizer type, HD, Adam, we have the activation type, tan, sigma, etc. And traditionally, we can use one-hot encoding to represent the categorical value using a binary vector between 0 and 1. However, one-hot encoding can mark 2 main drawbacks. First, it makes the search space large since it creates extra dimension, which is the multiplication between the number of categories and the number of choices per category. And when we have large number of dimensions, the optimization will be inefficient. Second, one-hot encoding mark the input space become non-continuous and non-differentiable. And again, the optimizer is inefficient when running on the non-continuous space. So you can see that they are challenging in optimizing mistype categorical continuous. And we are motivated to solve this challenging problem. In our first solution, we consider using Bayesian optimization to optimize the continuous input and multi-amp Bandit to optimize the categorical. Our intuition is from the recent success of multi-amp Bandit in sequential decision making under uncertainty for discrete and categorical input. Both multi-amp Bandit and Bayesian do exploration and exploitation to make a decision. But the question now is, how can we combine, how can we integrate these two powerful algorithms together? As the algorithm overview, we propose to optimize the categorical variable using multi-amp Bandit, and given the categorical variable, we condition and optimize the continuous using Bayesian. We evaluate the Blackbox to observe the feedback. Based on the feedback, we update and refine both multi-amp Bandit and Bayesian models. so that it can make better decisions in the next iteration. Particularly when using multi-arm Bandit to select the categorical variables, we need to define the arm and the reward probability for each arm. Here, each optimizer will correspond to an arm, such as the HGD will be the first arm, Adam will be the second arm, and RMS prop will be the third arm. The reward probability will be considered as the classification performance when we use HGD. And then multi-arm Bandit will balance between exploration, exploitation to select the best arms. And our intuition is that the high-performing optimizer will be selected more frequently than the others. But multi-arm Bandit also maintain a small probability to explore the unknown arms. Using that concept, we can scale up to handle multiple categories. Each category can have multiple choices. After selecting the categorical variable H using multi-arm Bandit, we now utilize Bayesian to find the corresponding variable X. We need to define the joint kernel for both domain, categorical and continuous, and among several choices for the kernel, such as the additive or multiplicative form. In our recent ICML 2020, we propose to integrate these two forms together, and we found this perform well in practice, where we have a hyperparameter lambda to balance between these two forms, and we can estimate lambda directly from the data. Next, let's move into the advanced setting in mixed optimization on how to deal with high-dimensional input space. And what do I mean by high-dimensional input space? Suppose that we need to optimize a Blackbox function with 200 dimensions, let's say 100 dimensions for continuous and 100 dimensions for categorical. It is notorious that high-dimensional setting will cause serious problems for most of the optimization methods. There are two major difficulties. First, it is the statistical challenge, since the input search space grows exponentially with the dimension. It makes the optimization difficult. The second is the computational challenge, since we rely on the global optimizer to optimize the acquisition function to select a next point, but the global optimizer may fail to return an optimum within limited time and resource. To overcome these challenges in high-dimensional setting, one of the ideas is to use local trust optimization, where we can create multiple trust regions across the search space. Then we perform local optimization in each trust region. Here, the local trust region is smaller and narrower than the original space for the local optimization to be successful. And using the local trust optimization framework, we're gonna iteratively expand the search space for exploration, narrow down the search space for exploitation, or terminate and randomly jump to another location if the local search is exhausted. As I mentioned earlier, the key idea in local trust optimization is that given limited observation, it seems to be impossible for the Gaussian process to perform a highly accurate prediction in the original space. But if we narrow down into a smaller area, then the GP estimation will be more accurate, and by that way, Bayesian optimization can be successful. Recently, as ICML 21, we extend the local trust idea to handle mixed categorical continuous input, where we need to maintain separate trust regions One is for categorical and another for continuous, defined from the best since observation. And after a local search is exhausted, we allow to select a new trust reason using UCB principle, where we balance between exploiting the promising reason versus exploring a new reason with high uncertainty. And in our algorithm, we again iteratively expand, sync, and restart the local search. And in particular, if after a repeated failure, we're gonna narrow down the search by iteratively, or if we got repeated successes, we're gonna expand the search by for exploration. And we perform this adaptation on both spaces for categorical and continuous. And I would like to emphasize that this idea is natural to be extended for handling parallelism, where we can use multiple agents or multiple machines to perform the optimization jointly. In the last part of the talk, I'm going to talk about another interesting direction in misoptimization for population-based automated reinforcement learning. Population-based training is one of the successful methods proposed by DeepMind in 2017. And the high-level idea in population-based training is that it's gonna maintain multiple parallel agents. Each agent will train a single neural network, and particularly each agent will receive a different hyperparameter to train a neural network. And we don't know which hyperparameter is the best here, but we can keep track of the performance at different iterations. And by doing that, the poor performing agent will be terminated, and the high performing agent will continue. After terminating the poor performing agent, we restart them by copying a network weight from the best performing agent and generating a new hyperparameter by randomly perturb from the best agent. And at the end of this single training process, we obtain the well-trained deep learning models. And I would like to emphasize that this happened during a single training process. We don't need to retrain the model after the termination. There are two key advantages of population-based training in hyperparameter tuning. First, it can learn a schedule of hyperparameter over time. For example, it can identify the good behavior to be selecting large learning rate at the beginning and smaller learning rate at the later stage. On the other hand, most of the existing hyperparameter optimization method will only consider a fixed set of hyperparameter over the course of the training. So here, PBT will be more flexible because it can adapt the hyperparameter on the fly. The second advantage will be time efficiency. In the existing method, whenever we change the hyperparameter, we need to retrain the deep learning model from scratch. But here in PBT, we don't need to retrain the model. It just happened in a single training run. So you can see that PBT will be more time efficient than the existing method. We notice that in the PBT principle, it relies on random search to select hyperparameter. So recently, we proposed the BB2 population-based Bandit, which is the extension of PBT using Bayesian optimization. And our intuition is that using Bayesian will improve the performance rather than using random search. Particularly, the hyperparameter update is controlled by time varying Gaussian process Bandit optimization, where the final reward in reinforcement learning application can be represented as the improvement between two consecutive time steps. And by using that representation, we can show the equivalent between maximizing the final reward versus minimizing the cumulative regret in the Bandit setting. And our population by Bandit has been successfully deployed in RayTool library to solve real-world problem. So now user can import our packet, PBT packet from Ray library and try it in a few lines of code. One of the drawbacks of PBT is it's only applicable for continuous variable. So we continue the success of PBT by extending it to handle mixed categorical-continuous input. Particularly, we look at the time-varying and parallel extension to the existing framework, where I have mentioned that we can use multi-amp Bandit to optimize the categorical variable and Bayesian to optimize the continuous. But we to the best of our knowledge, the time-varying and parallel multi-amp Bandit doesn't exist in the literature. In our paper as NeurIPS 2021, we propose a new time-varying and parallel multi-amp Bandit to optimize the categorical. And for that extension, we start with the ESP3 algorithm, which is a popular algorithm in multi-amp Bandit. Then we have the ESP3.m is the parallel extension for ESP3. And what we have been doing is we make the time-varying extension for the ESP3.m. And in our algorithm, we assume that the reward output is time-varying. We also derive the upper bound on the cumulative regret. We saw that it grows sublinear with the number of iterations. We have successfully utilized the proposed method in tuning deep reinforcement learning applications. In particular, we optimize the data augmentation type as the categorical variable, as well as the continuous hyperparameters such as the regularization, PPO clip, learning rate, and entropy exploration. Takeaway: throughout the talk, I have presented to you one of the exciting research directions in Blackbox optimization with categorical and continuous input. So we want to optimize the Blackbox function f, where the input variables include the continuous and the categorical. And I have presented 3 methods to solve this problem. In the first method, we talk about the idea of using multi-amp Bandit to optimize the categorical variable. And given the categorical variable, we optimize the continuous using Bayesian, and we repeat that process iteratively. The second approach is to deal with high-dimensional settings, such as when we have 200 dimensions. We're gonna use the local trust region idea to consider the smaller input space, and we perform local optimization in each local trust. And we maintain 2 local trusts, one for categorical and another for continuous. The third approach, we talk about the hyperparameter optimization in deep reinforcement learning. And in particular, we look at the population by method, where we maintain multiple agents in parallel. Each agent will train a single deep neural network, and we terminate the poor performing agent and update the hyperparameter using the parallel and time varying Bandit and Bayesian optimization. They are the references for the talk, as well as the implementation for reproducibility. I hope the topic in Blackbox optimization with mixed categorical continuous are useful to some of you. I'm happy to take suggestion, question, or if you want to collaborate, feel free to drop me an email. Thank you very much.